So our next speaker is Richard Warburton from Switzerland, Basel University, and the title of his talk is "A Bright and Fast Source of Coherent Single Photon." Hi, Richard, and the screen is yours.
Thanks very much, Pascal. Pascal, bonjour. Can you hear me okay?
Yes, we can hear you perfectly fine, and you can see your screen as well. It's good.
Okay, so everything's good. And I don't have a laser pointer, but I do have my mouse. Can you see that?
Your mouse.
Yeah, okay, very good. Okay, thanks very much, Pascal, for chairing the session. Thanks very much to the Institute of Physics for organizing this nice meeting, and very grateful to the organizers to give me the chance to present our work here. Pascal, I think you've heard this talk before. You might want to go and get a coffee, but let me get started. So, in case I run out of time at the end, let me thank all the very talented people in my group here in Basel. I don't have time to list their various contributions, but they've all contributed in fantastic ways to this project. We've had some local theory support in the Sangoa group, and in this semiconductor business, nothing is possible without really nice semiconductor heterostructures, and we get really beautiful material from Arne Ludwig and Andreas Wieck in Bochum in Germany. So a huge thanks to them. So this talk is about single photons, and a photon at optical frequencies is the only known way, I would say, of transmitting a quantum state over a long distance. So this means it plays a crucial role in quantum communication, quantum key distribution. There are already implementations of that, of course, but there are more sophisticated protocols that would be very nice to implement at some point. So a device-independent quantum key distribution would be one, and then quantum communication with more complex quantum states of light, for instance, cluster states. And if you go further, then you can do more with photons. You can implement quantum simulation protocols. For instance, boson sampling, and boson sampling is an interesting example because quantum advantage is arguably on the horizon. And then if you can create such nice states as, for instance, two-dimensional cluster states, then you could attempt to implement something like measurement-based quantum computing. So from a semiconductor point of view, let me give semiconductors a plug. What I've shown here is the design of a vertically emitting laser. So these devices are really important in our technology these days. So what you have in this device, you have a top mirror. This is made out of a heterostructure of two different materials to create a Bragg mirror. You have a top mirror and a bottom mirror to form a cavity. You have an active region, in this case, a handful of quantum wells. These have a very strong oscillator strength in the optical regime, and you can create a population inversion by sending a current through the device. So as you can see, there are N and P-type contacts. So if you run a current through this diode under forward bias, you can create a population inversion here. And so the heterostructure design is quite sophisticated, and once you have that, you can do some post-growth processing. Here, a mesor's been created, some oxide layers coming in from the side. These funnel the current into this small region in between, and these things work beautifully. And in the meantime, they're very cheap, they're very small, so you can switch them on and off very quickly. So there's a huge toolbox there in semiconductor technology, and you'd like to exploit that in the quantum domain. What we were missing back in the old days was a quantum emitter, something that plays the role of a single atom. In the meantime, we have such elements. These are called self-assembled quantum dots. And I've shown a picture of one here. This is a slice through a quantum dot. Beautiful TEM image from our collaborators on the material side. And what you see here is the indium arsenide quantum dot. This is very small, around 10 nanometers high, around 20 nanometers in base length. So you replace the semiconductor bands with confined levels. And these quantum dots then play the role of single emitters in our experiments. So the dream, and our chair has actually pushed this forward probably more than anybody else, is to create a single photon source based on a single quantum dot. The idea is you have some device, you send in a trigger, for instance, a laser pulse, and then this device should produce per laser pulse one single photon at the output. And in an ideal world, you would create one photon and only one photon per trigger. The photons should be indistinguishable. Sometimes we call that coherence. So the photons should be the same in every degree of freedom, one to the next. And the device should be 100% efficient. So for every laser pulse, you get one photon. And ideally, this should operate at a high repetition rate. And another point on the wish list is you have something that's future-proof, so you can use related technology to create entangled pairs, cluster states, and so on. So obviously, such a device does not exist, but a lot of progress has been made recently. And let me just flash this up. This is some old work of ours. These are quantum dots in a bulk sample. And what we're doing here is a resonance fluorescence experiment. So we have a coherent laser. We tune the laser across the quantum dot transition and measure the intensity of the scattered signal. And from this, you get a line width. And so this is a slow measurement. This captures pretty much all the sources of noise that you have inside the semiconductor. And for many years now, we get line widths which are reasonably close to the transform limit. And this tells you that even in this complex semiconductor environment, the noise is low enough that you can generate coherent photons. And in fact, in the second plot here, I've shown the line width as a function of the scanning frequency. And what you see is if you record such spectra on a time scale of perhaps 10 microseconds, something like that, the line width comes down. And in fact, we get line widths that are within 10% of the transform limit. So this measurement tells us there are some noise sources, but they're slowly fluctuating and they're relatively easy to deal with. So to get these nice properties, our own recipe here in Basel is to use resonant excitation, that for sure. We have the benefit of very high quality material, but also the design makes a difference. In our experience, putting these quantum dots inside a diode makes a difference. So are these quantum dots electrically contacted? In fact, the quantum dots operate in the Coulomb blockade regime, so the charge on the quantum dots is locked. Okay, so you'd like to make a single photon source. A quantum dot in the bulk sends photons pretty much in every direction. What you'd like to do is channel all those photons into one optical mode. One way to do that is to put a quantum dot inside a resonant cavity. And this is a picture from a famous review. This describes the options. So one option is to put a quantum dot in a so-called micropillar. This is a Fabry-Perot type resonator with lateral confinement provided by these sidewalls. And as our chair has shown, these can have extremely nice properties. If you come at the problem from an atomic physics background, then the cavities that they use tend to be traditional Fabry-Perot cavities. These are macroscopic curved mirrors here, which confine the light. And there seems to be a trade-off here. You can have a very small cavity with a modest Q factor, or you could have a very large cavity with an extremely high Q factor. And we wanted to try and create some device which has a reasonably small mode volume, but an extremely high Q factor, the best of both worlds, as it were. So inspired by the atomic physics approach, we decided to take the concept of a Fabry-Perot cavity and then scale it down. So our device actually looks like this. We have a semiconductor heterostructure at the bottom. Here's a semiconductor mirror. There's a layer of quantum dots towards the top. And then we complete the cavity with a dielectric mirror. Here it is on the top. The radius of curvature here is around 10 microns, so this is highly miniaturized. And the separation between these two mirrors is also around a micron. The mirror itself here is a dielectric mirror, and it's possible to create extremely high reflectivity mirrors using dielectric materials. And in this quantum dot business, we never know exactly where each quantum dot is located in the XY plane, and we also don't know exactly at what frequency a particular quantum dot will emit. Our solution to that problem is to make the device tunable in situ, and the way we do that is lock the position of this top mirror, and then we move the bottom mirror in the lateral plane to make sure that a particular quantum dot lies at the center of the optical mode, and then in the Z direction to make sure that a quantum dot comes into a frequency resonance with the cavity mode. So that's our device. We build these things, cool them down to 4 Kelvin, and run our experiments. One detail for the semiconductor specialists, we really like putting our quantum dots inside a diode structure. This means including an N-type region and a P-type region in the device. This is not obviously compatible with a high Q optical cavity, and the reason is that these highly doped layers absorb, and we get around that by putting these doped layers at the antinodes, at the nodes of the vacuum electric field in order to reduce the absorption. And according to literature values, the P-type contact is the main source of trouble. We make this very thin, and we put it here at the node of the vacuum electric field. Okay, so our experiments from a couple of years ago, we use the best top mirror that we have or is possible to create in actual fact, and we run our experiments, and this gave us cavities with extremely high Q factors. Our quantum dots also operate in a very nice way. The charge is locked by Coulomb blockade, and the optical line widths are quite close to the transform limit. And then we see a very clear signature of strong coupling. Let's take just one example, perhaps the one here on the right. So we're operating here with a positively charged trion. Here we make sure that the trion energy is constant, and then we tune the cavity energy or cavity frequency by changing the distance between the two mirrors. On the y-axis, this is the laser frequency with the laser we use to probe the eigenstates of the system, and you see this very nice anti-crossing when the quantum dot and the cavity come into a frequency resonance. So you can determine the vital statistics from these spectroscopy measurements. So when the quantum dot is out of resonance with the cavity, you can measure a line width, and that tells you the cavity Q factor. We have around 500,000 in this experiment. And then when the quantum dot and the cavity are on resonance, we see these these mixed states, the polaritons, and the splitting here is twice the coupling, and gamma is also deduced from this line width. Here the parameters, so the main point is that the coupling is bigger than the cavity decay rate and considerably bigger than the exciton decay rate, and the bare cooperativity is above 100. So this is a very nice result. That's spectroscopy. It's nice to see the behavior of this coherent quantum dot cavity system in the time domain. And to do that, we measured the autocorrelation function. And if you do the right things, you can see very, very nice oscillations in the autocorrelation function. And this is a vacuum Rabi oscillation. These oscillations correspond to a transfer of a quantum of energy from the quantum dot to the photon and back again to the quantum dot and so on. And you can see we have 5 or 6 oscillations before they decay away. Exactly how this works, this is the Jaynes-Cummings ladder. What we do in this experiment is we tune our laser so that we drive a 2 photon resonance from the ground state to this 2- state. When the 2- state emits a photon, because of the nonlinearity in the Jaynes-Cummings ladder, it puts the system not into an eigenstate of the system. That gives us a quantum beat, and then this decays by emitting a second photon. And this is an example of the beauties of quantum optics, how you can probe this dynamics via the autocorrelation function. And demonstration that this is indeed the mechanism comes from the G2 at time delay 0, which is around 80 in this experiment. This tells you that you're scattering photons in pairs. So that might be the basis potentially for a photon-photon gate, but that's hard. We're a long way away from that. We wanted to do something a little simpler in the meantime. So we wanted to use this technology as a single photon source. And the way to do that is to drop the reflectivity of the top mirror. The previous embodiment was over-engineered in this sense. The photon rattles around inside the cavity pretty much until it's scattered, and this reduces the outcoupling efficiency. So you want a cavity, but you don't want too high a Q factor. The Goldilocks regime, this optimizes the outcoupling from an exciton in the quantum dot to a photon exiting the cavity when the cavity decay rate is equal to twice the coupling, the Goldilocks cavity, as I've called it. So that's what we did. Same heterostructure now with a semiconductor mirror with a lower reflectivity, and this is how the experiments proceed in the lab. I would say we can tune the cavity by changing the distance between the 2 mirrors. We can also tune the exact frequency of the quantum dot by the bias we apply to the diode. And you can tune the thing up so that the quantum dot exciton is in perfect resonance with the cavity. That's what's shown here. What we then do is leave the gate bias as it is, sweep the cavity frequency, measuring the decay rate, and you can see the decay rate here goes up, and down again. So this is a clear Purcell effect. So the decay rate is strongly enhanced when the quantum dot exciton is in resonance with the cavity, and out of resonance, the decay time matches the decay time in the bulk. That's around 500 picoseconds for these quantum dots, and on resonance, the decay time comes right down to 50 picoseconds. This corresponds to a Purcell factor of around 10. An important detail is that the cavity mode actually splits into 2, one H polarized and the other one V polarized. This splitting is around 50 gigahertz in this experiment. Okay, so photons are coming out of the device. You want to characterize them. Firstly, what's the photon purity? to what extent you create one photon at the output and not, for instance, 2 or 3 photons. So that's something we probe in the standard way, recording the autocorrelation function, equivalently the anti-bunching. And we find that the G2 at time delay 0, it's not 0 as it should be for a perfect single photon source, but it's reasonably small, 2% in this particular experiment. It's very, very important these days to create coherent photons, indistinguishable photons in the language of quantum optics. And we probe that with a 2-photon interference device. So we create 1 photon in this experiment. 1.5 microseconds later, we create another one. We bring these together at a beam splitter, and we measure to the extent to which these 2 photons interfere. And in the experiment, you can manipulate the polarization. You can put these 2 photons into orthogonal polarization states to suppress the 2-photon interference. Then you put them into the same polarization state to measure the 2-photon interference. And here we see very, very nice 2-photon interference signature. And the metric for that, the visibility, is around 97% in this particular experiment. And I would say this is a result that reflects the low noise in our experiment. The Hom visibility here, this is the visibility of the 2-photon interference, is plotted as a function of the delay between the photons. It's not simple, but relatively easy to get high values at very short values of the delay. There, the noise processes are unlikely to be fast enough to contribute. It's much harder to get high 2-photon interference visibilities at high delay. Here you really start to probe the noise inside the semiconductor. And if you dream a little bit, then if you can create a photon every nanosecond or something like that, and you can get the efficiency very, very high, then you can create a very large number of photons before the coherence starts to decrease. So what about the efficiency of this device? That's what I've shown here. So the system is tuned up in the lab to make sure that the quantum dot is located at the center of the cavity mode, and to make sure that the quantum dot is in a frequency resonance with the cavity. We then increase the power of the laser step by step. The signal goes up. This is the linear regime. Then you reach a maximum and it comes down. This is a complicated example of a Rabi oscillation. We obviously put the laser power at this maximum, and then we probe the signal we have coming out of the device. So let me just take a moment to explain how this works. We have such large signals at this point that our single photon counters, single photon detectors cannot detect all the photons. So we have to deliberately attenuate the beam. We do that. We put in an absorbing filter which attenuates the signal by a known amount. So actually what we measure is this count rate here. We have a detector which has an efficiency of around 80%. And what I've plotted here, this is the count rate we would get if we had a perfect detector. So this is a detector with 100% efficiency, and a detector which could cope with this high flux of photons. So this gives us a signal here of around 40 megahertz. The repetition rate of our laser in these experiments is something like 76 megahertz, and this means that we have an efficiency of 55%. What that means is we send in a laser pulse into our entire experiment. The probability that a single photon exits the final optical fiber of our device is 55%. So that's very nice. It's not 99%, unfortunately, but it's certainly very nice. We've done some analysis what reduces this from 100%, and this is the bottom line, as it were. So we send in a laser pulse. What's the probability that we create an exciton in the quantum dot? That's what I've called pi. And by modeling these Rabi oscillations, we can calculate that, and that turns out to be about 96%. This exciton then decays and creates a photon. What's the probability that the photon goes into the H-polarized cavity mode? This turns out to be around 89%. Then when the photon is in the cavity, what's the probability that it emerges through the top mirror? That's around 99%. So the combination of these factors gives us 85%. So we think that the main limitation at the moment is simply in our experiment itself, getting these single photons from the cavity all the way through the optical system to the final optical fiber. So this suggests, in actual fact, is this classical optics that we should work on first. These numbers are really quite promising. This puts single photon sources into some sort of context. Parametric down conversion is a stochastic process and clearly has its limitations in quantum technology. With quantum dots, you can create deterministic single photon sources. There are a number of ways to do that: planar waveguides, bullseye structures, micropillars. I think I would like to add our open cavities to the list. And I think the overriding point, two overriding points. One is quantum dots at low temperature can be extremely nice single photon sources. They can create a very high flux of coherent single photons. So no matter how you do that, provided you can keep the noise in the device to a low level, then the properties of the photons are extremely nice. The second overriding point, if you want to do implement some boson sampling algorithm using single photons, then this efficiency, the scaling is probably something like the efficiency to the power of the number of photons you're working with. So incremental advantages in this efficiency create orders of magnitude difference to these success rates. Okay, so let me come to my conclusion. Actually, this is more of an outlook. Where do we go next? How do we have a very nice single photon source. How do we make it better? How do we make it more user-friendly? These are projects we'd like to work on. And then we'd like to use similar technology, but also combined with spin control to create spin photon entangled pairs and ultimately cluster states. And I think these are very, very exciting prospects for the future. Okay, so I've come to the end of my talk. Thanks very much for listening. Thanks very much for your attention.
Thank you so much, Richard, for this beautiful talk and beautiful results. We are a bit late, but you have some questions, so let's try to be efficient. The first one is about your perspective, your prospect for using the same technology to couple two quantum dots to the same cavity mode or to two coupled cavities. And in a similar way, also, you know, this work that we've done in my group in the past to couple two cavities to do the exciton by exciton cascade to have entangled photons. What is the flexibility that you can foresee for your platform for these different kinds of ideas?
Oh, okay, that's a good question. I think conceivably you could couple two quantum dots or possibly more to the same cavity mode. Obviously, the coupling is best if both quantum dots and the cavity all have the same frequency, but you can actually tolerate some detunings, and perhaps it might be possible to tune the relative detuning with some lateral gates or something like that. The idea of the bi-exciton cascade, there you would need two cavity modes, which are quite different in frequency, one to interact with the bi-exciton, the other to interact with the exciton. I think that would be principle impossible. You would have to use, for instance, an excited cavity mode, one of the lateral modes, and you would ideally have to choose the right radius of curvature to match the frequency difference. Perhaps there's another perspective, though. Once the cooperativity is actually very high, then you could create the bi-exciton, and then in the presence of these cavities, it could well decay by emitting a two-photon state with both photons at the same frequency. That would be a nice way, I think, to create a number state when n equals 2. These photons would not be entangled.
Maybe another question about the phonon-Seibon suppression due to cavity quantum electrodynamics.
Yes.
Paper that we did a few years ago, we showed that actually to get even higher indistinguishability without filtering the photons, it would be beneficial to increase the fineness of the not the fineness, the Q factor of the cavity.
Yes.
Changing the length, and basically you would keep the same Purcell factor, but you would have a narrower line width. Have you explored that? Do you think of exploring that?
That's a very good question, and we haven't explored that. If I reinterpret the question a little, then what limits our Hom visibilities here? Is this phonon? Is this a phonon-related process, or is it something else? And experimentally, we don't have an answer to that question. If it would reduce the phonon scattering by increasing the Q factor, then we could certainly do that. And in fact, this we're operating actually at where kappa is not exactly 2G. Kappa is actually bigger than 2G, and this kappa equals 2G is a very, very broad maximum, as it were. So there would definitely, I could imagine we would get hopefully a very, very similar photon flux if we also worked with cavities with a higher Q factor.
Thank you, Richard.